We're continuing our conversation of symbolic function composition by finding the domains of the two previous composite functions we found. And that should actually say from example 5, because that was the example that we were just working on. So I've just kind of copied for us again what the functions were. The original functions were f of x is square root of x minus 2, and g of x is 3x squared minus 1. And the first stage in our f of g of x was to simply plug in the g of x, which is this formula, into the place of x in the f function. And we were able to simplify that to the square root of 3x squared subtract 3. So when we're thinking about this function composition, what's really important for us to think about is two things. Whatever the names of our inside and outside functions are, we first need to make sure that whatever x value we plug in is something that's allowed in the original inside function. So we're just going to call these inside and outside functions. And then whatever we get out of that would be some expression involving x. So this is, let's just call it a k of x, since I don't want to tie it to particular actual functions. So whatever comes out is going to be some expression involving x. And then we need to think about whether or not that entire k of x is something that I can put into, so fits into the domain of this new outside function. And if all of that works, then we are good to go in terms of domain. So looking at this first example, my inside function, g of x, has no domain restrictions. It's a polynomial. So when I'm thinking about, are there any restrictions of x values I can put into the inside function? Well, no. So there's no restrictions to start when I do the function composition on the left here. So then what I need to do is I just need to examine the final function and think about, are there any domain restrictions on this? So do I have any domain issues here? And I do, because this is a square root function, and with a square root function for our domain, we need whatever the radicand is, 3x squared subtract 3, to be greater than or equal to 0. Well, I can go ahead and factor a 3 out, and I get x squared subtract 1. And then I could factor, and I have x subtract 1, x plus 1 is greater than or equal to 0. And I'm just going to think about what this radicand looks like. It looks like a parabola with a y-intercept of negative 3 and x-intercepts at negative 1 and 1, and it is concave up. So this is what my radicand looks like. And we can see that this radicand will be positive anytime it's above the x-axis, which would mean for x's from negative infinity to negative 1, and then from 1 until infinity. And now we'll go ahead and we'll check our answers in Desmos. So what I've got here is I've got the original f of x entered in function notation, I've got the g of x entered in function notation, and then I asked for the f of g of x. Notice the f of g of x is the green function here, which is really the function that we're trying to figure out. So this function right here, it does appear that its domain matches what we wrote down here, negative infinity to negative 1, union 1 to infinity. I do have the function f of x plotted here. It's a root function shifted to the right 2, and then this is my g of x, 3x squared subtract 1, which is just that a concave up parabola, but what we're really focusing on is this green function and its domain. Okay, let's take a look at our other example here, my g of f of x, and I've got the first part started here, and we talked about this a little bit when we did this example on the previous video, the idea that this square and the square root don't fully cancel. So we need to go back and we need to think, okay, the f of x, that's my inside function now. What are the values of x that are allowed to be plugged into that? So for this one, the f of x domain would be taking the radicand of the f of x and setting it greater than or equal to 0. And that tells you x is greater than or equal to 2. So before I even start this problem, I know that x has to be greater than or equal to 2 to even be able to do this function composition. So now I can go ahead and simplify and say this is 3 times x subtract 2 subtract 1 if x is greater than or equal to 2. This gives me 3x subtract 6 subtract 1, or 3x subtract 7. And again, this is only valid if x is greater than or equal to 2. Now I examine my simplified function composition and see if there are any further restrictions on the domain as a result of the composition. And there are not, because this is just a linear function, so no further domain restrictions. So we would just write our domain as x greater than or equal to 2. And then we'll go ahead and check in Desmos. So I have these same functions plugged in, the f and the g. I've go ahead and turned off those graphs so we don't have to look at them. So really we're just trying to focus on the g of f of x part, which we saw simplified to, it's getting a little messy here, 3x subtract 7 with a domain of x greater than or equal to 2. So we can see that the domain does appear to be everything from x greater than or equal to 2. So right here, this is the point 2, negative 1. I can also see that this does appear to be a line with slope of 3. So if I were to continue it and just follow that slope down, I would have a y-intercept here at negative 7, which matches what this simplified form looks like, but the line only starts from x greater than or equal to 2. So its domain is based on, from this original f of x, the inside function, I needed my x to be greater than or equal to 2 in order to even do the function composition. So the main thing that you should be getting out of domains of composite functions is first you're going to check the domain of the inside function, and then you're going to check the domain of the simplified composition. And we didn't show an answer where you got answers from 2 of those, but then you're going to take the intersection of those 2 answers. So you're going to combine those 2 answers together. And I'll show you an example of this on the next slide. I know this is kind of a long video already, but I think it's a good example for you to see. Okay, so I have an example here where we have our f of x is the root of x minus 1, and our g of x is 1 over x minus 1, and we're going to do g of f of x. So 1 over, and then I'm putting parentheses where the x is, and I'm just going to plug in the f of x, which is root of x minus 1 in here. And that doesn't really simplify too much. I can just drop the parentheses, so 1 over root of x minus 1, subtract 1. So now I need to go back and I need to think about what's the domain of this f of x function, so the inside. So the domain of the inside function is going to be found by taking the radicand and setting it greater than or equal to 0, which means x is greater than or equal to 1. So I'm going to box that out. And now at this point we need to look at our composite function and figure out what its domain is. So domain of our simplified composite function. So on the composite function, since it's a rational, or it's a fraction, we need the denominator, root of x minus 1, to not equal 0. So we're just going to go ahead and solve that equation. We're just solving it like a normal equation, so I'm moving the 1 over to the other side, and then I'm going to square both sides. So root of x minus 1 squared, which does just give us x minus 1 as long as x is greater than or equal to 1. That's usually not a step that we think about when we're solving because it'll come out in the check. And so x cannot equal 2. So I need to now put those 2 answers together. So I'm going to think about a number line here, and I'm going to put my 2 important numbers on there, 1 and 2. And I need all of the x's that are greater than or equal to 1, which would look like that, but not equal to 2. So that means my domain would be from 1 to 2, not including the 2, and then from 2 until infinity. And what's going to happen at 2 should be a vertical asymptote, because that will make the denominator equal to 0, which is what causes a vertical asymptote. And we can check just by putting this into Desmos. So as you can see, I've plotted the function in Desmos. I've got my original f of x, my g of x, my g of f of x, and we can see that my domain does start at x equals 1, so this is the point 1, negative 1. But then at x equals 2 right here, we have our vertical asymptote, so our domain from left to right goes from 1 until 2, not including 2, and then from 2 until infinity.